So, we discuss some applications of Serre-Frenet formulas, and first of all we observed that we can compute the higher order derivatives of R using Serre-Frenet formula. Now, what we do, we consider a special vector which we call Darbox vector, which is a vector in the rectifying plane, that is a linear combination of T and B. If we choose the component as torsion and curvature, then this vector is a interesting vector. So, what we will be doing, I will be considering the cross product of this Darbox vector with our vector T, N and B. So, first let us compute the cross product of D with T. So, while computing the cross product, the first term will go off and the second one will become K into B cross T, and B cross T will be N. So, this becomes N, K N, and K N you have seen is T dash. So, this is an interesting relation. So, first Serre-Frenet formula can be expressed in terms the Darbox vector. So, this is another version of the Serre-Frenet formula, that T dash is nothing but D cross T. Now, similarly you can check the cross product of D with the principal normal N. So, in the right side of the box relation, you will be getting tau into T cross N plus K into B cross N T cross N is B, it is known to us, plus K B cross N will be minus T. So, minus K T. So, this becomes formula number 2 of Serre-Frenet. So, I can say this is in fact N dash. So, I can rewrite this second Serre-Frenet formula, which says that N dash is in fact D cross N. And lastly, consider the cross product of D with the binormal B. So, this is D means tau T plus K B, and its cross product with B will give me tau into T cross B. Cross product B with B will become 0 and T cross B is minus N. So, this becomes minus tau N. So, that gives me the third formula of Serre-Frenet. So, the third one, that is B dash, can be written as, this is B dash in fact. So, the third one can be written as D cross B. This is another version of Serre-Frenet formula in terms of the Darbox vector. Okay. Now, I move on to the fundamental theorem of calculus, space curves. So, fundamental theorem of space curves. So, let me write down the formal statement of the theorem. It says the following. The statement is this: if two single valued continuous function, if two single valued continuous functions let us call them Ks and tau s. They are functions of a parameter s, and s is a variable which is non-negative, in fact positive, are given then there exists one and only one space curve. There exists one and only one space curve determined except for its position, in a space for which S is the natural parameter K is the curvature function, and tau the torsion, and tau is the torsion. So, this is the complete statement of the fundamental theorem of a space curve. So, in order to prove it, first we will ensure the existence of 3 unit orthogonal vectors. So, to prove the theorem, we first ensure the existence of 3 unit orthonormal, in fact orthonormal. When I say orthonormal, I need not write down unit. 3 orthonormal vector fields. I am saying vector field. All variable vectors are called vector fields. The vectors whose components are functions which vary in a space are called vector fields. So, I will call T and B as vector fields. T, N and D. Once their existence is ensured, theorem is almost proved. Okay, so, what I will be doing in order to ensure the existence of these 3 vectors, I will consider a system of differential equation. So, consider a system of ordinary differential equation, as this. Let me consider these differential equation d alpha over ds equal to k times beta. K and tau are given continuous functions. So, I am thinking of a differential equation in the functions alpha, beta and gamma. So, 3 unknown functions are there, and d beta over ds equal to tau gamma minus k alpha, and d gamma over ds equal to minus tau beta. Okay. These functions alpha, beta, gamma are vector valued functions. So, ordinary differential equations can involve functions which are scalar valued or vector valued. Now, these 3 differential equations will have solutions if and only if we assign some initial values. So, what I will do? I will assign the initial values as. So, these equations, differential equations of course, will admit unique solutions if there are initial values. There are initial values which we choose as follows. Okay. I will choose alpha at 0 equal to a unit vector t. I will call it a unit vector t, and beta at 0 as a unit vector n. Okay. And gamma at 0 I will choose a unit vector b, where t, n and b are 3 orthonormal unit vectors, where t, n and b are 3 orthonormal vectors. I am not calling them vector field, I am calling them vectors at s equal to 0, corresponding to the parametric value s equal to 0. I have chosen these 3 vectors. Now, this provides, this box condition provide the initial values for this differential equation, for this system of differential equation, and therefore, with these initial value, this differential equation will admit a solution. Solution means there will be vector fields alpha, beta and gamma, okay, which will satisfy these equations. And if you look at these equations closely, you will see they are nothing but the Serre-Frenet formulas. Okay. Okay. I can rub off the upper part. Now, I can construct a function. Okay. Now, we can define a function. Now, we can define a function of s. Now, we can define a function R s as follows. Okay. I will give some value to R s 0, and R s I will define as R as 0 plus h times R dash as 0 plus h square upon 2 factorial R double dash as 0 plus h cube upon 3 factorial into R double dash as 0 and so on, triple dash, and the next term will be h to the power 4 upon 4 factorial fourth order derivative at s 0 so on. This is how I put forward the definition of a function of s. R as 0 I can assign any value, and then this function is well defined if these things are known. Okay. So, what I will do, I will choose my function R s in such a manner that R dash as 0 is t at 0, okay, or you simply call them t still. Okay. And their higher order derivatives will be nothing but a linear combination of t, n and b. So, if you want to see them, it will be R as 0, which is a scalar, plus h times t at 0, okay, plus h square upon 2 factorial. R double dash means R double dash is this k n plus h cube upon 3 factorial. R triple dash is here, this is minus k square t plus k dash n plus k tau b plus so on. So, everything, yes, all of them are vectors. All these things are vectors in fact. Okay. So, you see in the right side you go on writing the derivatives, and you will notice that everything is a linear combination of t, n and b, and these t and b exist because they are the solutions of these differential equation, and therefore, rise the function R s is well defined. Okay. Once the function R s is well defined, it is equivalent to saying that a curve exists. This is the function of a single variable s, so which exists, and therefore, a space curve exists whose curvature is k and the torsion is tau. Why k is curvature, tau is torsion? Because they satisfy the Serre-Frenet formula. These are nothing but Serre-Frenet formula. So, we get a space curve. So, theory of ordinary differential equation guarantees the existence of t, n and b. Since these differential equations are Serre-Frenet formula, these scalar quantities are nothing but the curvature and torsion. So, this determines this expression, this determines a space curve whose curvature is k, ks, and the torsion is tau s. When I say that this system of equation has a solution, what I am saying is that alpha, beta, gamma as functions exist, and alpha, beta, gamma you can consider as vector fields t, n and b. So, these three ordinary differential equation with these initial values guarantee the existence of a curve. So, what you see in this theorem is that Serre-Frenet formula have a fundamental importance. They ensures the existence of a curve. So, this is the proof of the fundamental theorem of space curves. So, in fact, last time I left one exercise. I don't know whether you are able to solve it or not. If you haven't done it, I can do it because I am left with some time. Okay, still I have some time, so I can solve those. 10 minutes I can solve that exercise. Okay, so the problem that I left for you was, yes, if all the tangents of a curve pass through a fixed point, then that curve is a straight line. This is what we have to prove. We can easily visualize this fact, but we need to prove it. So, let me rewrite the exercise. Okay. If all the tangent lines pass through a fixed point, if all the tangent lines of a curve pass through a fixed point, then the curve is a straight line. Okay. So, let us consider a curve C which has this property, that all of its tangent pass through a fixed point. So, let me draw it here. So, suppose this is a curve, and if you draw a tangent, it passes through a fixed point whose position vector I am calling as r0. So, this is some tangent line drawn at the point rs. So, any other tangent also pass through it. All the tangent pass through the point r0. Okay. Okay. So, I can write down the equation of a tangent line. So, equation of a tangent line, of an arbitrary tangent line, of an arbitrary tangent line. If you are considering an arbitrary tangent, means you are considering tangent line at an arbitrary point of the curve. So, that must be written as r equal to rs plus some lambda times t, unit tangent t, or you can write down r dash if you wish. Okay, no problem. Now, this lambda is what, if you remember, when you write down the equation of a line, this scalar is actually called the parameter, and if you see it geometrically, it gives you the distance from the point rs to the point r0. This is the lambda. Okay. Now, this distance will vary. Okay. So, this depends on the parameter of the curve. So, lambda is not fixed, it will vary according to s. So, lambda is not a scalar, in fact it is a function of s. Okay. So, an arbitrary tangent line will have this type of equation. So, now since it passes through, a fixed point r0, we have r0 equal to, all of them are vector quantity. I forget to mention the bar. So, that is R s plus lambda s into t. R 0 satisfy this, means this. Okay. Now, I will differentiate it with respect to s. So, differentiating it, we get the derivative of the left hand side will be 0 because it is a constant vector, and the derivative of this will be r dash s. R dash I can write down as t plus derivative of lambda is lambda dash s, t as it is, plus lambda s as it is, derivative of t is t dash. Okay. You can take t common from the first two terms, this is equal. You take t common between the first two terms, so it will be 1 plus lambda dash s into t plus lambda s into t dash. Now, I will take dot product with t dash in both sides. So, left hand side is 0, so it will remain 0. So, taking dot product with t dash, in the above equation, you will be getting 0 equal to when t and t dash are taken dot product. So, it will become 0. Okay. Okay, just a minute. So, this is 0 and I will be getting lambda s into t dash. So, norm of t dash square, and t dash we know is k n. So, or you can say it r double dash. So, lambda s into r double dash equal to 0. Okay. R double dash, if you remember, is what? It is the curvature. So, or I can say that lambda s into the curvature k equal to 0. So, this implies either lambda s is 0 or k is 0. When k is 0, it is a straight line. This implies a straight line. Okay, so, our assertion is proved if k is 0, and if lambda s is 0 means the point r 0 lies on the curve. Okay, so, if you draw a tangent such that it passes through the points of the curve, then that is always a straight line. So, this also implies a straight line. So, in any case, you see that the curve becomes a straight line if all of its tangent pass through a fixed point. That completes the solution of the problem. So, I stop at this point.